Thank you. It's a huge pleasure to actually be giving an in-person inaugural lecture. Yeah, what did they say? Start date 1st of April 2020. That will be fine, they said. Little did I know. So it's great to be able to go and talk to you in person. So I say an inaugural lecture. This is probably less an inaugural lecture, more an attempt to try and make sense to myself of the weird twists and turns that my career has taken. So I will talk about some polymer physics. I'll just select a bit of a strand of research that's taken me through my career. But I'll also talk about some work I've done around the relationship between science and society, and I'll also talk about particularly science and innovation policy. And as I say, I will try to make a narrative that links all these three things together, and you'll see how successful I am. But I want to start just by mentioning one of my favourite, I'm going to start by talking about macromolecules, what makes macromolecules move around. And to kick off, I'm going to start with one of my favourite novels, the book The Third Policeman by Flann O'Brien, one of Ireland's greatest absurdist modernist novels. And anybody who hasn't read this book, you should. It's a fantastic, disturbing, very funny, dystopian book. But it has a really interesting line in weird science. And its plot revolves around a policeman who rides a bicycle. And at one particular moment, the policeman talks about the atomic theory. And he says, "Did you ever discover or hear tell of the atomic theory?" The sergeant inquired. Everything composed of small particles of itself. They're flying around, never standing still or resting, spinning away and darting hither and thither and back again, all the time on the go. These diminutive gelatin are called atoms. So this essentially is the essence of Brownian motion. You know, this is what the world is like at the atomic or molecular level. Stuff's moving around all the time. Then he goes on to draw an important conclusion from this. The net result of this is that people who spend most of their natural lives riding on iron bicycles over the rocky roads such as this parish get their personalities mixed up with the personalities of their bicycle as a result of the interchanging of the atoms of each of them, and you would be surprised at the number of the people in these parts who are nearly half people and half bicycles. And of course, having spent 15 years of my life in Cambridge, that's a kind of sentiment I kind of can sympathise with. But it's marvellously absurd, but it does pose the question, okay, why don't we? Why don't riders merge with our bicycles? What are the driving forces that cause things to mix, things not to mix? So I'm going to talk about how fast macromolecules move around, and that's about molecular mobility. But the key question I want us to focus on now is, what are the driving forces for molecular diffusion? What makes things want to mix? What makes things want to unmix? So diffusion, this process by which if you put two things together, the atoms merge and mix with each other. Very familiar kind of experiment you do if you just put a drop of ink in some water. Eventually you get from this inhomogeneous state to this homogeneous state. So when you get taught about this, you know, your first encounter with diffusion, you get shown a diffusion equation. Diffusion equation tells you that the flow of molecules is proportional to the concentration gradient. So the system tries to equalize all the concentration gradients. Of course, that's fundamentally not quite right. Fundamentally, what's really important is the second law of thermodynamics. This diffusion process is a manifestation of the second law, and that's about maximizing the entropy of the universe. And as we know, as we teach our students, if a very slick way of satisfying that condition of maximizing the entropy of the universe is to think about the free energy of a system and to think about free energy being minimized. So in fact, although the simple diffusion equation says that we should think of diffusion as being driven by a gradient of concentration, so we have a flow of molecules flowing downhill, really, what we should think about is this as a chemical potential gradient. So molecules flow down a chemical potential gradient. Chemical potential is essentially the free energy per molecule. So mostly, this doesn't really matter. Chemical potential is related to the derivative of the free energy with respect to concentration. And most of the time, they say more or less the same thing. So if the only thing that made any difference here was the entropy of mixing, None of this would make any difference. And in fact, you can convince yourself that the two formulations of diffusion are completely equivalent. But there are two special cases. One is, and one I mentioned just because it was important in my career, but it's not actually particularly important more widely. It's quite interesting. You can have very favourable interactions between strongly miscible polymers. You get anomalously high diffusion driven not by entropy but by enthalpy. But a much more important condition is where you have unfavourable interactions leading to phase separation, and there you have a diffusion coefficient that is negative, and I'll explore what that means in a moment. So of course the key factor of people and bicycles is that they have an unfavourable interaction, and so they don't in fact mix. I just mentioned the anomalously fast one because this is what I did my PhD on, so it's interesting that in that way. And really it just follows, because if you write down the second derivative of free energy, you get this term here which has got an n in. So chi is a number which is of order 1, and it's negative if the two things want to mix. So the factor you've got an n in there can make this term much bigger than this term, which is essentially the entropy. So actually in miscible polymer blends, diffusion can be much faster than you'd expect in the normal run of things, and it also has a very strong concentration dependence. But what's interesting about this equation is that if chi is greater than 2n, 2 over n, the diffusion coefficient turns negative. And this means that the flow of molecules, the concentration gradient, is the opposite direction to the chemical potential gradient. And so, whereas, just as I've always said, molecules want to flow from high chemical potential to low chemical potential, in this case, that corresponds to molecules flowing the wrong way, from low concentration to high concentration. You get this negative diffusion coefficient. And this leads to this beautiful classical mechanism that was first identified by John Kahn many years ago of spinodal decomposition. And essentially what's happening here is any fluctuation that you get in concentration, so if you start out with a uniform mixture, any concentration fluctuation you get is magnified. Imagine you get a little concentration fluctuation due to the randomness of Brownian motion, then you get a little dip in concentration, material flows from low to high, and it magnifies that concentration dependence, and that's how you get phase separation, and you get this length scale selection mechanism, which comes about because large scale fluctuations don't grow very quickly just because stuff's got to diffuse a long way. Short wavelength fluctuations are suppressed by the fact they lead to too much interface, so you get this single wavelength. So that's by way of background. What difference do having surfaces and interfaces make? So most of what I've done over many years has been to focus on the effect of surfaces and interfaces on this kind of process. And the first thing I'd say is, in a mixture, if you take two things, one of them is bound to have a lower surface energy than the other, just because that's the way things are, and that you'd expect to drive segregation of one component to a surface. And it turns out this effect is really important for macromolecules, much more important for macromolecules than for small molecules. And what we find is the presence of surfaces and interfaces can lead to new mechanisms for, say, phase separation. So wetting and surface-directed spinodal decomposition that I'll come to in a moment. So that leads to this idea of spontaneous layering in thin films, which is what I call self-stratification. So I mentioned what I did in my PhD. In 1987, I went to Ithaca, to Cornell University. And I'm going to dwell on this a bit, because this is my sole claim to be a materials scientist. These 2 years I spent in Cornell Material Science Department were, before now, that's when I was a materials scientist. And I just, a few things, I just found some photos to remind myself of Ithaca, the State Diner, open 24 hours. Often find myself in there at 3 or 4 in the morning. For some reason, our group only had the 10 p.m. to 4 a.m. slot on the accelerator. So every Thursday evening, we'd spend that time, and then we'd go to the State Diner. And the State Diner at 5 a.m. in the morning was a fantastic cross-section of American life. Marvellous. Ithaca is a very beautiful place. This is actually my walk to work from downtown Ithaca up into Cornell University, which is on the height. It has waterfalls flowing by, and it had hard winters, so then it froze. And there indeed is a picture of me when I was less nesh in those days, enjoying the frozen waterfall. And that's something that's Kinder Downfall's not quite like that. But the most important thing about Ithaca was Ed Kramer, my postdoc mentor at the time. So Ed was a fantastic scientist, died in 2014, and I learned so much from him. He was always very happy to give me advice throughout my career. Quite a lot of his advice was don't ever do anything administrative or managerial, which I failed to follow. But there we are. He was great otherwise. The two bits of science I did learn in Cornell were these. One is just the stress that surface and interface effects are really important in thin films. So, again, to go back to this idea, if you have a mixture of two things, the lower surface energy stuff will want to go to the surface. So if you've got a glass of gin in front of you, the surface of that glass will have more alcohol in than the bulk, because alcohol's got a lower surface energy. But this is quite a small effect. But for polymers, it's really big. So what we found here was, in this case, the only difference between these two polymers is one's hydrogenated and one's deuterated. So it's simply the difference between a CH bond and a CD bond. A very small polarizability difference, probably worth less than 0.1 dynes per centimetre in terms of surface energy. This isn't enough to make the deuterated stuff go to the surface. So for reasons that we understand, that I won't have time to go into, the polymeric nature really amplifies both the scale of the size of the effect, how much segregation you get for a given surface energy difference, but also the length scale, how far into the bulk that does. So this is actually ion beam analysis. So this is showing you depth profile of 100 nanometers. So it's quite a long range effect. And then, to go back to this idea of uphill diffusion, if you have a polymer that has, one component's got a lower surface energy, what happens is that you get the low surface energy stuff goes to the surface, it makes a hole. Now, because there's a hole and the diffusion coefficient is negative, now stuff starts diffusing out of the hole and makes the peak behind bigger. So you end up with this idea of a composition wave, if you like, growing into the surface. So this exemplifies this idea of self-stratification. This is a computer simulation, that you get this one or two layers of pure material just form by themselves. And so I'll come back to this in more complicated circumstances. So in 1989, I went to Cambridge, and I just want to mention two people in Cambridge. One was Sam Edwards. Sam Edwards was the great theorist of polymer physics, actually was a lecturer in Manchester, in the University of Manchester, in the physics department, went to Cambridge from Manchester, but basically was the author, I think, of modern polymer physics. Really impressive and frightening figure to work with in some ways. But he was, what I learned from him, he was a great servant to the science system. He was a chief scientific advisor for the Ministry of Defence. He was pro-vice chancellor in the University of Cambridge. He was a head of SCRC. And I think I did learn from him about the importance of that kind of work outside one's own scientific interests. The other person I should mention is Athene. Athene Donald's still a great friend. I learned so much from her, mostly actually about working on biological systems, which I'm not going to talk about at all, but I learned a huge amount from her about experiments and doing them, and actually having the confidence to work on messy systems, I think, is what I learned from Athene more than anything else. And so this took me to think about, okay, we have ordering processes in thin polymer films, phase separation, self-stratification, this idea that by controlling, so when I say a thin polymer film, typically you'd make a polymer film with a solvent, you put a solution of polymers down, the solvent would leave, that would drive a phase separation process, or indeed a crystallization process, and you'd get some morphology that was strongly influenced by the interface. So, for example, found in this very simple case of just you take two polymers, mix them in a solvent, spin coat them. What do you get? What you get can show two things. You can get phase separation in the plane, but you can also get this layering parallel to the surface, so-called self-stratification. So Mark Gagan was one of my early students who showed this. So what difference does this make? It turns out this actually is a very attractive single-step route to make bilayer films that have useful functional properties. And so in Cambridge, in Richard Friend's group, Anna Arias, who was one of Richard Friend's students, discovered this phenomenon in the context of polymer photovoltaics. Henning Seringhaus, likewise, in polymer field effect transistors. Anyway, I moved to Sheffield in 1998. There's a picture of the physics department looking down from the maths department, looking down from the maths department onto the physics department. That, of course, is entirely correct and proper. And looking across over the scruffy, lovely scruffy town that is Sheffield. And I had a great time in Sheffield. One of the reasons I had a great time is I worked very closely with Tony Ryan, who many of you will know as a former UMIST materials science lecturer. And in fact, going to Sheffield was a little bit of a combination of two things making me go to Sheffield. One was the prospect of working with Tony, because I realised lots of the things I wanted to do needed more chemistry than I know. And also, the slightly hillier environment also played a part, I won't deny. So I went there with this idea, okay, we know you can get interesting and useful effects by having thin films that phase separate, and the phase separation is modified by the surface or the interface, and you could get something useful. But what we need to know is what's going on when you're doing this, you know, what's actually happening in the process. And so we built a device that allowed us to study what was happening during a spin coating process. So James Sharp was a student and then a postdoc. He's now a lecturer in Nottingham. Did the great job of making this what we lovingly called the optospinometer. Basically an instrumented spin coater that allows you to look at light scattering in situ as you make this film. And this made, Sasha Herriot was the postdoc who produced this very, very nice data. What's going on is not at all obvious, but the key point I want to make is you can see this kind of data tells you two things. It tells you how much, as the solvent leaves, the film thins, and you can follow the thickness as a function of time, essentially by counting these fringes. These fringes come from interference from the light being bounced off the front and back. And you can see what's happening laterally by the appearance of a scattering peak. So you see a scattering peak. And we were able to interpret that and come up with a model that showed us what was going on. And what we actually find is that in these systems, they all self-stratify to start with. And the question, do you get a self-stratified film at the end or not, is really a question of a secondary instability. So you get this secondary instability where the layers break up and you end up with the phase separated result. Now, if you know the mechanism, then you can start to say, can I modulate this? Can I change the conditions so I can get the structure that I want? And another great student, Parvane Makarian, who's now in Trinity College Dublin, was able to show that you could suppress this instability, and so you could, if you like, turn off and on self-stratification. Okay, so what was the use of this? Why is this interesting? Well, one of the great applications of this at the time seemed to be an organic solar cell. So you can make a solar cell, most solar cells are made out of silicon, but you can make a solar cell out of plastic. So you can make two polymers, a donor polymer and an acceptor polymer. The way this works, light comes in, makes a photon comes in, makes an electron-hole pair. The electron-hole pair needs to be split so you can get the hole to one electrode, the electron to the other. And it's a feature of polymers that the exciton binding energy is really quite high. It's much higher than the exciton binding energy in silicon. And so what this means is this only works if you've got an interface so that the exciton goes to the interface and then it gets split because the two polymers have got different band gaps, essentially. But the problem is the excitons can only diffuse about 7 nanometers before they recombine. So you've got to make a structure in which the exciton can find an interface to be split apart within 7 nanometers. So what you want to do is you need to find really quite a complex nanostructure that's going to make itself, because you don't want to be messing around trying to put different layers on. You just want to kind of spread this out and get it spontaneously to form this layer. And indeed, we did loads of work understanding this relationship between processing, the morphology you get, and then the performance that you get. And if you do that, then you can kind of design a processing route to optimize performance. Okay, if I was giving this talk 10 years ago, this is what I would have said. And I know this because I pinched this slide from the talk I gave 10 years ago. The argument we all had was that organic solar cells would replace silicon because you can make them really cheaply in large volumes. So silicon is made, you know, it's a batch process. Making a lump of single crystal silicon is a difficult batch processing business. The world output at the time was only a few square kilometres, and if you want to really decarbonise the energy system, you're going to need, you know, thousands of square kilometres. And you contrast that with printing. You know, every day, well, in those days, you had newspapers still, and so you would print out quite a complex pattern. You know, hundreds of square kilometres would come out of a single plant. So that was the argument, but I was wrong. We were all wrong. And what has happened in the subsequent 10 years is this, that the cost of silicon solar cells has fallen exponentially. It's fallen, well, quite nicely on this learning curve plot. As the cumulative installed PV capacity has increased on this logarithmic scale, so the cost has fallen. And so what this teaches you, what we should know, one should never underestimate the power of incremental innovation in an incumbent technology. So in a way, all that effort by many groups around the world, many failed startups in fact, founded on this premise that we could get organic solar cells more cheaply than silicon. I think at this point we realised that was all a doomed enterprise. So what do we do with that kind of all that knowledge that we got? Well, if you can't beat them, you can join them. So the question then comes, can we improve the efficiency of silicon solar cells? So we step back. The maximum efficiency of silicon solar cells is actually about 29%. It's kind of a physical law. It comes from the Shockley, it's called the Shockley-Queisser limit. And where this comes from is this. Sunlight there's a kind of spectrum of colours that come out of the sun, which is expressed here. And it turns out for a silicon solar cell, or indeed actually any semiconductor solar cell, the long wavelength stuff is not absorbed. So the semiconductor has a band gap. That's, if you like, the minimum energy that's needed to promote an electron from the valence band to the conduction band. So if the band gap, if the photon energy is less than a band gap, nothing happens. It's not absorbed. On the other hand, at the blue end, the energy is absorbed, but then the electron is very high in the conduction band, and there's nothing stopping it just dissipating its energy as it falls back to the band edge. So up here, this stuff is absorbed in the blue light, lots is absorbed, but you lose lots of energy. And so it's only really the energy around the red for silicon where you get efficient absorption. So this suggests, okay, if you could convert blue light to red light, you'd break that limit and you'd increase that efficiency to about 35%, which 6% on the scale of solar cells is quite a big deal. So my colleagues in Cambridge had a way of doing this. Actually, after I finished being a PVC at Sheffield, I went to Cambridge for a bit of a sabbatical. And so Akshay Rao and Richard Friend took me by the hand and taught me that you could, in principle, do this. The way it works is this. If you've got an organic semiconductor, you can get a blue photon, comes in, makes an electron-hole pair. And this is a singlet. The spins are pointing in opposite directions. Now, for reasons that I don't fully understand, I'm not sure they do either. Under some circumstances, this singlet will split into two triplet excitons, which have half the energy. Now, if this happens in a bulk organic semiconductor, well, nothing very much happens. The triplet excitons can't recombine to make a photon because of the selection rules that come about from their spin state. So they just sit around doing nothing and eventually decay non-radiatively, so it's wasted into heat. But what Akshay and Richard realised is that if you put next to this a quantum dot, an inorganic semiconductor nanoparticle, where you match the band gap to these triplet excitons, then the electron and the hole can hop into there, they can transfer the energy, and there they can happily recombine, and they can make two red photons with half the energy. So the great thing about this is that every step of this way is actually, in principle, 100% efficient. So this, in principle, is a way of doing 100% down conversion, efficient down conversion. Of course, you've got to make the thing, and this is where all the stuff about process and surfaces and interfaces come in. So this is the kind of cartoon that we draw. You know, one draws cartoons for research proposals. And in fact, this was indeed the very cartoon I drew for the proposal that we wrote about how to do this. And you can see the marvellous sketch about how you need to kind of get in the nanoparticle. You need to control the ligands, the molecules that are in contact with the nanoparticle that stabilise that. You need to control that. You need to get good dispersion, all that sort of stuff. And you need to be able to do this. The idea is that you just make a little film of this that you just layer onto your silicon solar cell. Blue light comes in, gets converted into red light. So you can kind of do this cartoon of what you want the molecules to do, but you actually have to design some processing routes to do that. This turns out to be quite a big, this project of trying to make a photon multiplier turns out to be quite a big thing. Quite a lot of people are now involved. It's chemistry to make new singlet fission materials. It's essentially Hugo Bronstein's group at Cambridge does that. You need photophysics. So Akshay and Richard do the photophysics. You need to make the quantum dots. You need to get the chemistry right of making the quantum dots. Then you need to kind of mess with. So the quantum dots come with a particular coating. You need to be able to change that coating so you get good contact. You need to characterize this processing morphology property relationships, and that was the role of me and my old friends in Sheffield. And we want to commercialise this, so Cambridge Photon Technology is a spin-out in Cambridge that's been created to commercialise this. So the sort of thing that you see, just to give you a very brief flavour of it, if you look at it, here's a sample. You mix up the quantum dots with the organic semiconductor, just spread it out, what do you get? This is actually a map of the photon multiplication efficiency. And so material scientists will, or anybody who's certainly done any polymer science, will immediately recognise this. This is a spheruolite. This is spherulitic growth. So you've got in the middle there, you've got an aggregate of quantum dots. A spheruolite grows from the aggregate. Just like zone refining, the organic semiconductor thinks the quantum dots are an impurity, so it just spits them out. And you end up with this very non-uniform distribution of quantum dots where you've got big aggregate in the middle, a kind of coffee ring around the outside, and then better dispersion in the middle. So just to bring this up to date, again, to get a handle on this process and control it, we need to do some kind of in situ X-ray scattering so we can follow the process as it happens. And Dan Toolan, the postdoc, is doing that. Okay, so I want to change gear with the tenuous connection I'll now make. Okay, so this is a genuine piece of nanotechnology using lead sulfide quantum dots. Let's wind back to 2003 or so. Nanotechnology was just coming up to being, people were very excited about it, but people were worried about it. And indeed, there was some controversy. A controversy sparked by our new king. So Prince Charles in 2004 warned against the little-known science of nanotechnology, the next big scientific controversy after genetic modification. And so at the time, I got very much involved in this. So I just started for reasons that, I ended up working with a social scientist, Stephen Wood, to write this report for ESRC. then I got very much involved in, okay, the idea at the time was if we want to avoid a big controversy, we need to involve the public, we need to talk to the public about this before technological paths are set. So we had citizens' juries, this thing, the Nanotechnology Engagement Group, tried to gather all this work about public engagement, which actually I think was very worthwhile and did produce some interesting and good results. And no, maybe it's not too much to say, you know, there wasn't a great public controversy about nanotechnology, and I think, you know, part of the reason for that was I'd spent so much time trying to persuade Greenpeace that actually this was quite a cool way of making new solar cells and they should thus be in favour of it. But my kind of original interest in nanotechnology came from more radical visions, and it really arose. I wrote a book called Soft Machines, Nanotechnology and Life in 2004. And this was really a reaction against a vision of nanotechnology that was very prevalent at the time and hasn't actually gone away, which was this idea from Eric Drexler that nanotechnology would look like the principles of mechanical engineering applied to chemistry. So you've got all these pictures of kind of, you know, cogs and gear wheels made out of atoms and molecules. And, you know, for reasons that I could spend a lot of time talking about, I think this is fundamentally wrong and fundamentally draws the wrong lessons from biology, and I got involved in a number of kind of quite public debates about this, which was all very entertaining. Where does this idea, so that biological nanobots could repair and improve the human body was the kind of, you know, one part of this Drexlerian notion that we'd have these little submarines sailing around in our bloodstream, mending us and making us live forever. So where did this idea of little biological submarines come from? Well, one great place was, of course, this marvellous film, Fantastic Voyage. I'm sure those of us of a certain age will have seen Fantastic Voyage. It's kind of a mid-80s film. The premise was fairly ridiculous, so I believe some scientist had a blood clot in his brain. The entire free world depended on being able to fix him. A crack team involving Raquel Welch and some others were shrunk down to a tiny size, injected into the bloodstream. All kinds of excitement transpired. I think this was the film that launched 1,000 nanobots. And still, you know, this is the kind of vision that you see. You still see these kinds of pictures that illustrate articles about nanotechnology. This kind of fertility enhancement one is a particular classic. I should say, and of course these are all ridiculous, and I'll say why they're ridiculous in a minute. People with interested cultural history actually know that this goes back a little bit further. I believe the first reference to nanosubmarines was actually in this science fiction short story, Waldo, published in 1942, which was actually by Robert Heinlein, though he was writing under a pseudonym at the time. And there's a fantastic and fascinating story about how this idea of a nanosubmarine came out from science fiction into kind of, you know, the sort of futuristic visions. It's a story that involves the Nobel laureate Richard Feynman, the Satanist Aleister Crowley, and the rocket pioneer Jack Parsons. It's fascinating, but I haven't got time to talk about it, so I shall move on. Anyway, did they get the science right? Of course they didn't get the science right. You can't shrink people down. But there's something really interesting about the way, about, you know, what's wrong with this vision. I mean, you do show, any scientific audience will see pictures of these nanosubmarines and say, that's ridiculous. But it's quite interesting to say why it's ridiculous. And, you know, here's my sketch of why it's different. You know, physics looks different when you're small. That's the fundamental reason. So, you know, viscosity dominates, you're buffeted by constant Brownian motion, you get these strong surface forces, and anybody who's involved in biomedical materials will know that anytime you stick one of these things in the blood, it will get coated with proteins. That was, in fact, the one bit. There's a great scene in Fantastic Voyage where Raquel Welch gets coated by proteins, and it's the one bit that you think, actually, the science there was accurate. I just want to focus particularly on this question of how you move around. And there's this lovely piece of physics, this great article from Ed Purcell a while ago, saying that, you know, the crucial thing here is Reynolds number. So in fluid mechanics, if you think about, if I try and swim through water, what stops me going forward? It's actually two physical things that stop me going forward. One is the fact that water's got inertia. It's heavy and you have to move it out of the way. And the other is that it's got viscosity. There's a kind of internal friction when you move layers of water past each other. And Reynolds numbers tells you what's the ratio, which is most important. And it has this form, it's the size times the velocity times the density divided by the viscosity. And the key thing in here is it's got this size in it. So if I go swimming in a swimming pool, the Reynolds number is probably 10,000 or so. So you're in the inertia-dominated regime. But as I shrink myself down to the size of a bacteria, viscosity dominates. So the way to think about, if you really were Raquel Welch shrunk down to microscopic sizes, it would feel like you were immersed in a giant vat of treacle. And that's really significant because the strategies you use for swimming at high Reynolds number don't work at low Reynolds number. And in particular, there's a beautiful thing. The low Reynolds number fluid mechanics is time reversible. So you know that anything where, any kind of simple swimming stroke, if you go down, you push forward. If you come back up, you just go back again. So you have to do something to break time reversal symmetry to make any progress at low Reynolds number. I spent a long time with Tony Ryan actually thinking about, oh God, how could we make a submarine that worked? But the answer came from a brilliant theoretical physicist called Raman Golestanian, who came to Sheffield in the late 2000s. Raman's he's now at the Max Planck, one of the Max Planck Institutes, but he is a fantastically clever and marvellously creative scientist. And he came up with this idea. He said, okay, imagine you've got a particle and you coat one half of it with a catalyst. And then you have a reaction where you have, this is my physicist view of a chemical reaction. I've got things that are two blobs and the reaction makes them split apart. And so you get this catalysis. What happens is that if you've got a chemical reaction that produces more products than reactants, what this does is it makes an osmotic pressure gradient, because osmotic pressure is a pure colligative property. It only depends on how many molecules you've got, not how big they are. What this means is you get an osmotic pressure gradient that will push the particle on. So this seemed like a beautiful, simple and marvellous, compelling idea. And Tony and I thought, well, actually we can make this work. Here's how we could do it. We could just take polystyrene, half coat it with platinum, take a simple reaction, hydrogen peroxide, splitting that up. You start with 2 molecules, you get the 3 molecules, end up with 3 molecules. It ought to work. And John House was our postdoc at the time. He's now I think he's now a professor of chemical engineering at Sheffield. Actually got this to work. So here's how this works. So here are our particles. So this is 4 particles. So if you like the contrast, the top left one has no catalyst. The bottom ones have got the catalyst. Left have got no fuel. The right have got fuel. And you can see this one that's got both a catalyst and a fuel. And it bobs along quite satisfactorily by itself. So this all works marvellously. And there's a kind of typical time trace. And so, we can analyse this all theoretically. Raman had a fantastic theory of this is called self-diffusiophoresis in the trade. Diffusiophoresis is the motion of a particle driven by a concentration gradient. This proved to be a very kind of lots of people then carried on with this kind of experiment, and it's a kind of a big industry of self-motile particles. So I'm going to change gear yet again. Having talked about radical nanotechnology, I want to talk about when I was having these discussions with these followers of Drexler in the early 2000s, they were saying, this technology, it will just accelerate so quickly. By 2020, there will be no material shortages because we'll have nano devices that can do everything. And indeed, there's a very famous book by Ray Kurzweil called The Singularity is Near, which said combination of nanotechnology, artificial intelligence, genetic engineering would make this accelerating pace of technological innovation. And indeed, Kurzweil said that by 2045, in fact, we would have achieved the singularity in which essentially we'd have all have uploaded ourselves into our iPhones and we'd have merged with our devices, and we'd all be immortal and things would be totally different. So there's a singularity. So this is going to happen in 2045. And, you know, I can't help noticing that, you know, it's now 2022. We're pretty much halfway towards the singularity. It doesn't really seem to be happening. So the other alternative is that, you know, that Tyler Cohn, the economists kind of start to say, well, wait a minute, it looks like technological innovation is actually slowing down. It seems like, you know, we're getting into this economic mess. And so I did, you know, this is kind of what prompted me to think about, you know, economics. And indeed, if you look at the economic data, it really doesn't, this does not look like a graph that's heading towards a singularity. So this is actually productivity, labour productivity. So this is the UK economy, how much output in value, real value, the UK economy produces for an hour of labour. And this is the current version. So you saw from 1970 to 2008, a 2.1% annual growth. We had a global financial crisis in 2008, and rate of productivity growth has fallen off a cliff, and it's currently 23% lower than it would be. And, you know, I would argue that this is, you know, the most important graph in modern, you know, in British economic policy or you know, politics. I think, you know, in a sense, everything that we've seen in the last few months has been the short-term unfolding of this trend. And I was, of course, very tempted to look at this other graph, looking at how much research and development the UK does, how R&D intensive the economy has been, and attempted to draw a connection between those two. So my first introduction to this world was really in writing or being on the steering committee to write this document, The Scientific Century, which came out in 2010. And essentially this was a pitch that was, you know, the Royal Society's pitch to say, don't cut the science budget. I guess at that time, you know, I came at this with the kind of fairly naive view that scientists have, that there's some, you know, simple relationship between spend more money on research, preferably in places like Manchester University, and then, you know, prosperity will pop out. This was a very interesting project, though, because it was James Wilsden was then the head of policy at the Scientific Century, who's, you know, a social scientist rather than a natural scientist. And there was a real tension between the kind of Royal Society view that just put more money into basic research and we'll all be fine, and James's attempt to actually get some evidence to do this. And it also had Lord Sainsbury and William Waldegrave were also on the committee, each of them saying how marvellous the other one was, which was quite interesting politically, and, you know, how this approach went on. But I mean, so in a sense, this sowed a seed of doubt in my mind that things were that simple, and I learned from other people, including Kieran for that matter, that you know, things were not, you know, that there was more to it than this. Well, the productivity recovery never arrived. This plot just shows you, I think, how slow economists were to understand that things had changed. So this plot shows, this is the OBR, so we're all waiting for the OBR forecast. So the OBR had this fantastic set of predictions about how, so each year the OBR produced a forecast of where productivity would go, and there we are, 2010. Only actually in 2016 did they think, oh, God, maybe this is not going to happen. So this plot, I've seen nothing like this plot ever, apart from possibly the income projections for the Department of Physics and University of Sheffield when I was in the department. Which, the upturn never came. So I got involved in thinking about industrial strategy, and actually, so sometime around 2016, I got together with Diane Coyle, who at the time was a professor of economics here. We met through Twitter, I should say, also to be up to the moment. So this was a really interesting thing. I got to know Andy Westwood, another professor in Manchester, who is an absolute master of understanding the skills landscape, but also how politics works. We persuaded Kate Barker to chair this. Craig Berry, my colleague from Sheffield at the time was a political scientist. And so we wrote a bunch of stuff about what we thought industrial strategy ought to look like. And I guess this is the kind of, the lesson here is, two lessons here. One, it was great to work, I found it fantastic to work with Diane and Kate to try and understand a bit more about economics. It's great to work with Craig to understand a bit more about, you know, political science and how that operates. And Andy had this Andy was a SPAD in the late New Labour government. He was John Denham's SPAD in Bays. He just was fantastic at saying, how does government really work? And we managed to get the timing right because Theresa May had come along and suddenly industrial strategy was on the agenda. So we managed to get Greg Clark to come to launch this thing. And we had a bunch of recommendations that I think were helpful. And the government indeed produced an industrial strategy, which did indeed have some relevance to what we were, drew on what we were saying a little bit. So I spent a lot of time trying to influence the debate. Part of influencing the debate involves, you know, doing things like select committees. And I've got this picture here. So this is titled, What Has Science Policy Ever Done for Barnsley? And the reason for this is I was there giving evidence, you see Rebecca Rendine from UKRI there too, about what we thought about industrial policy and industrial strategy. And this lady here said, oh, I just read your blog, because I have a blog. I read your blog post called What Has Science Policy Ever Done for Barnsley? I was really interested in it because I'm the MP for Barnsley. And it was a really interesting moment because I'd written that piece possibly in a fit of pique about the Crick Institute and going past the Crick Institute. And I was spending some time in Barnsley, which is a very deindustrialised, very poor part of South Yorkshire. And it had at that time a very challenging head leader of the council who, you know, would say to us, well, you lot in Sheffield's been living off Barnsley's back for the last 400 years, and now you and your leafy university, what have you lot ever done for us? So I thought it was actually quite a profound question. It did make me think quite hard about innovation, diffusion, and that sort of thing. So the next, again, I've had a blog since 2003. I started it to try and sell my book, and it's completely failed. The aim of making me a kind of best-selling popular science author failed totally, but it's actually been enormously helpful in other ways. And while I was recovering from having my hip replaced, I wrote quite a long piece about what I thought we ought to do to solve the Barnsley problem and indeed the Sheffield problem. And so somewhere around November 2019, I got a phone call one evening from a guy who said, oh, I'm calling you, I'm from The Guardian. I'm just ringing you up because I just wanted to get your reaction from the fact that Dominic Cummings has just quoted your work approvingly in a blog. And this resulted in this marvellous headline, which I shall treasure. The Guardian had their own particular angle they wanted to put on this story. But it was actually enormously useful in terms of giving me a bit more... people wanted to talk to me a bit more than they otherwise did. And the thing I really wanted to focus on at this point was regional imbalances in R&D spending. So I wrote this piece with Tom Forth in 2020 called The Missing 4 Billion. And the key thing that this pointed out was if we look at R&D spending across the UK, so this is public and private R&D spending broken down by NUTS 2 regions, as they were in those days, and you can see there's three big bars on the right. That's essentially London, Oxfordshire, Cambridgeshire. So those three chunks absorb about 46% of all public funding. So he really wants to highlight that the UK system pours most of its money into the Golden Triangle, and you've got so Greater Manchester is down here. West Yorkshire is there. You go down even further to Teesside and Cumbria. And what's really striking about this is that if you now look at the economic performance across the UK, we have this very divided country. So in terms of productivity, most of the UK is actually, well, London, the southeast, parts of East Anglia, look like a Northern European economy. So they're comparable with bits of the Netherlands, Northern Germany, and so on. But the North, the Midlands, Wales, Northern Ireland, these look more like, this is looking more like East Germany. Actually, East Germany has surpassed the north of England, more like southern Italy. So we've got this very funny, this very odd situation where the investments the government makes in R&D, which we would think ought to support productivity growth, we put those in places that are the least, already the most productive. So this, again, this did have some impact, I think. So in July 2020, the UK government produced this UK Research and Development Roadmap, which I think for the first time acknowledged that this concentration took place and that we ought to do more to build on a wider range of UK R&D strengths. And the government then wanted to produce a strategy, so an R&D, the so-called Place Advisory Group was set up. And I was a member of this. So we tried to kind of produce a strategy to correct that. The strategy ended up being subsumed in the Levelling Up white paper. So I find it's always interesting to see the sausage-making process about how policy is made and departments pinching policies off other departments. But the Levelling Up white paper emerged. It really, combination of this and the increased science spending and the comprehensive spending review really seemed to say that there was a recognition that this imbalance wasn't healthy and should be corrected, and we got this mission to about increasing R&D spending. And indeed, there was a very specific recommendation that we'd have £100 million split between Greater Manchester, the West Midlands and Glasgow to do all these things that we wanted to do. So I think that there was some recognition of these issues that I'd been raising. So in Greater Manchester, we were able to be ready for this because I'd been spending much time making this argument. I said, well, you know, you need to change things. The only way that you could really change things would be to devolve R&D funding to local cities and regions. And if you said that in Carlton House Terrace or in Swindon, they'd say, well, yes, we understand, you know, of course we understand the principle here. But, you know, in practice, if we did that, if we gave money to the South Yorkshire LEP, they'd just spend it on roundabouts or hanging baskets, and you know there's no capacity there to make those decisions. So this is a very conscious effort to head off that argument and say, you know, in Greater Manchester we can get our act together, we can get the universities, business community, the combined authority to come up with, you know, a strategy and a framework for making good decisions about R&D. So that brings us up to date. We're just currently going through the process of trying to work out how to spend that 33 million. There's a long story I'm not going to talk about. Big chunk of that hopefully will a certain amount of that will contribute to materials, so it will be directly relevant to this audience. So that brings me up to date. The three weird strands of my career loosely covered. I'm just going to finish by saying I really want to say I've had loads of great colleagues over the years, many of whom I've mentioned, not all of them, graduate students, postdocs, collaborators. You know, funders are always important. And I do want to say, you know, it's been great fun to talk to STS people, to innovation studies people and economics. I've learned so much from them, and since the ones who are in the audience, I say I hope you've indulged my excursions onto your territory. I guess finally, I think between Ed Kramer and Sam Edwards, I would like to think that Sam was right and Ed was wrong on this point. It is important for some of us to occasionally try and be heads of departments and PVCs and work for research councils and try and do something to make an environment that will allow other people to do good science too. So I'll stop. That was my friends in Sheffield, February 2020, just before I came. We all went for a walk, so a bunch of my friends and colleagues from Sheffield who I'll miss, but it's great to be in Manchester. Thank you very much.